in past units done some transformations on functions where we change x properties and change y properties. But what happens when we combine functions? Okay, it's not a simple process of just understanding what the changes in x are and changes in y are like it was before. We need to analyze these slightly differently. So we're going to look at combining functions and seeing what they look like graphically. So here I have a function 3x squared minus 2x plus 1. It's a quadratic function, and we're going to combine it with a square root function. We want to know what happens to this and what does this look like. So the first thing we need to consider are the domain and range. And so we need to make sure we understand some basic properties of domain and range and how they relate to basic functions. And so we're going to look at square root functions, reciprocal functions, absolute value functions, and polynomial functions. And when we look at the domain of a square root function, there is a restriction. The restriction is it cannot be negative inside the square root. So that's going to affect the domain of a function when we combine it with something else. Same with the 1 over x. If we have an x in the denominator, we cannot have it equal to 0. We cannot have the denominator equal to 0. We're going to end up with vertical asymptotes. So that's going to give us a domain restriction. For absolute value, there's going to be no domain restrictions, and for polynomials, the same thing. There's going to be polynomials are valid for a domain of all real numbers. Now the range is going to be a little bit trickier, so we're going to do limited analysis on the range, but we should have some basic ideas of the range. So for example, when we talk about square root, we can't be negative. Okay, the square root cannot be negative, so the square root y values square root are only positive. When we talk about 1 over x functions, the y cannot equal to 0, and we end up with horizontal asymptotes. And that horizontal asymptote can actually be a position that can be moved around. For absolute value, we know that the y values must be greater than 0, must be above the x-axis. Okay, so those are some basic principles that we can look at. We are primarily going to focus on domain though. Okay, the range tends to be a little bit too complicated to do much analysis with, but we will do some analysis on the range. So here's an example where we have two functions, f function and a g function. F function is a square root function, g function is a polynomial. So we should first of all observe what the domain and range is for the function. So if I have the f, my domain restriction is that the inside cannot be negative. So I need to know the boundary point. In this case, the boundary point is going to be 3. And we know that 3 must be greater than or equal to, x must be greater than or equal to 3 to keep a positive value in the square root. And the range of this, since it has no vertical shift, it's going to start at 0, and y must be greater than or equal to 0. For the g is a polynomial, it's a quadratic, so x is going to be all real. So we're going to have no restrictions on the x. And then for the range, we know that it's going to be positive 2. So y is going to be greater than or equal to positive 2 because its vertex is going to be a positive 2 and it faces up. Now what happens when we put this together? Well, algebraically, when we put this together, we end up with x squared plus 2 plus square root of 2x minus 6. So that's what my function is going to look like. And then we need to establish domain and range. So for the domain, we are going to look at the domain of the two functions, and whatever is the most restrictive is going to be the domain. So since x's can only be greater than 3, when I input into these two parts, although I can put in negative 2 into here, I cannot put negative 2 into here. So that is restricted by the most restrictive part, which is square root. So the domain of the combined function is going to be the domain of the most restricted part of the function. So x is going to be greater than or equal to 3. Now the range we're going to for now do by graph. So we're going to graph this and look at the range. Okay, so when I graph this function, I'm going to use my graphing tool, and I end up with some kind of graph that pretty much looks like this. Okay, we know it starts at 3, and y is equal to, when x is 3, we end up with y is, I think it's 11. Okay, so 11. So, and it goes off to infinity. So the range from the graph, okay, this is from the graph, the range is going to be y is greater than or equal to 11. And just be clear, I got this from the graph. Okay, so we're going to use technology for the most part to do the range. However, I will mention that it can be done with some other analysis, and this is a little bit more complicated, but when we look at the domain of this function, we know that x is greater than 3, and we know that the square root part of this graph is always increasing. We call it strictly increasing. And from x is equal to 3, we also know that the parabola is strictly increasing on that domain that we're given. So if both parts of this function are strictly increasing, we know that the whole graph is strictly increasing, so the left edge, or the starting point x equals 3, must be the very bottom of the graph, and that's what we observed on our graph. And so we can use that left-hand edge point as our smallest y value, in this case it's 11, and the right-hand edge, which is unlimited all the way to infinity, becomes our right-hand value, or the maximum value, which is infinite. And so we can justify then this graph by using some properties of the graph that we know. In this case, we analyzed it by the increasing nature of this graph. This whole graph was strictly increasing, so the left edge would be the minimum, the right edge would then be the maximum.